Okay, chapter 7, the quantum mechanical model of the atom. In this chapter, we're going to get at what the current view of the atom actually is. There's a lot of stuff in here that you're probably not going to understand. There are a lot of things in this chapter that I don't understand. And we kind of just need to be okay with not being able to understand everything. So it kind of makes life interesting. Okay, so until the beginning of the 20th century, scientists believed that physical phenomena were deterministic, meaning what's going on with an object right now in part determines what will happen with it in the future. This is also called Newtonian Physics. It's the idea that it's the stuff we can see. I mean, you throw a baseball and you can predict where it goes, right? You hit the brakes on your car, you can predict what's going to happen. But work at that time by mostly physicists, actually, discovered that with these subatomic particles, the very, very small particles, the present condition does not determine future conditions. So when you throw a baseball, you can predict what's going to happen. You put baseballs in a pitching machine, you can predict what's going to happen. If you throw it the same way, it goes the same place. If you do that with electrons, you can't predict what's going to happen. The electron could go in an opposite direction that you throw it. They are unpredictable. So it will probably land in a different place each time. And that's disturbing. But this is what happens with the very small. So we call this the absolutely small or quantum world. And the behavior of these objects are very different from the large or the macroscopic world that we can see. And so we just have to be okay with it, right? Things that are far too small to see do not behave in the same way as things that are large enough to see do. So absolutely small particles like electrons can actually be in two different states at the same time. Now what does that state is not, California and Nevada. You can actually be in 4 states at the same time if you go to 4 corners, right? We're not talking about states of the United States. We're talking about conditions. That is if they are unobserved. When they are observed, that forces them to be in one state or the other. How does an electron know that it's being observed? That's kind of disturbing. How can it, I don't know. So an example is radioactive nucleus is one that will spontaneously shoot out a particle. An unobserved radioactive nucleus can be simultaneously emitting a particle and not emitting a particle, and you don't know which it is until you observe it. But it's doing both at the same time when you're not observing it. So electrons are very small. So just reinforce what we know about electrons with an analogy. Okay, so a single speck of dust, right? Very tiny. A single speck of dust has more electrons in it than the number of people who have ever lived on the Earth. Not just currently on the Earth, but ever. That's a lot of electrons in a speck of dust. We can't even get our minds around how small these are. Electron behavior determines much of the behavior of the atoms. And so it's important for us to look at how these atoms, these electrons in the atoms are behaving. We can't directly observe them. We saw some fuzzy pictures of atoms, right, made with a scanning electron microscope. But the electrons are so much smaller that we don't even have those sorts of images. And they are so small that when you observe them, their behavior changes. Even just shining a light on an electron changes its behavior. So this is a difficult problem, trying to figure out how electrons work. So have you heard of Schrodinger's cat? Okay, this is an interesting analogy. So this is a thought experiment, okay? No cats were harmed in this experiment because it wasn't actually done. And the point of Schrodinger's cat is not that a cat can be alive and dead at the same time, because it can't. It's to demonstrate how quantum strangeness does not translate into the macroscopic world. To give us an idea of how we cannot take these particle properties of the very small and apply them to everyday life, things that we can see. So we're going to watch a couple of YouTube videos. Because these guys explain it way better than I could.
This wouldn't be a YouTube channel without a cat video, so without further ado, we present Schrodinger's Cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I have answer, please?
Any thoughts about that one?
So something like that, the thought experiment,
Mm-hmm.
that in reality would rely on like Newtonian physics, so it wouldn't necessarily be like a quantum.
Right. The cat does not behave in a quantum way.
But if you were to restrict down to like a quantum scale, potentially it could be like a
Yeah.
superposition.
And we'll look at some experiments where electrons behave as particles and electrons behave as waves, and we can't tell what they're behaving like until we observe them. And so when they're not being observed, they're actually behaving like both. And that's possible for the very small, but it's not possible for something like a cat. So I've got another one about the cat.
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrodinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. Think to say, what now? My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand it. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioactives is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the sciences. So there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead, and an equally good chance that the vial hasn't been broken and the cat's just kicking it wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom is decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrodinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrodinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. Alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below, and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
So both of those channels on YouTube have a lot of cool science on them. I would encourage you to go check it out if you're interested. Okay, so any other questions or comments about Schrodinger's cat? My son has a great T-shirt. It's got a wanted poster on it, and it says, Schrodinger's cat, wanted, dead, and alive. Right. Obviously, a cat can't be dead and alive. So does this idea of something being able to be two different things at the same time bother you? Is that disturbing? It should disturb you. It disturbs me. And look at these quotes from these famous scientists that were involved in developing quantum mechanics. Bohr said, anyone who is not shocked by quantum mechanics has not understood it. Because if you understand it at all, you're going to be shocked. Schrödinger wrote, I don't like it, and I'm sorry I ever had anything to do with it. Right? He's like, man, I wish I'd never gotten involved with this. Too late now. Albert Einstein was one of the guys involved in this. He said, God does not play dice with the universe. He was involved in developing quantum mechanics, but he did not like it, and he attempted unsuccessfully to disprove it until he died. He was looking for a way to say, no, that's not right. Couldn't find one. So there we are. We've got quantum mechanics. The quantum mechanical model, although it is very difficult to get your mind around, it does explain the manner in which electrons exist and behave in atoms. It helps us to understand and predict properties of atoms that are directly related to what electrons do. And some of the things it can explain are, why are some elements metals and others are nonmetals? Why do some elements gain an electron to form an anion and others gain 2 electrons? Some gain 3. Why is that? Quantum mechanics explain. Why are some elements very reactive, others are practically inert, don't react with anything? And it also explains many other periodic properties that we see in the elements.